So in this question, we're given like some 100 millimeter samples of cross section having 5 meters by 5 millimeters, and each sample is tested in an apparatus which applies an increasing tension to the ends of the sample until it breaks. Okay. We're also given that the length of the sample is measured and a plot is shown. So that's the plot, and the results for five such samples are shown. Okay, so let's try part A of the question. So the first part of the question asks us which of the following samples is the stiffest when compared to the other samples. So what is stiffness? Well, if we recall for something that obeys Hooke's law, so F equals Kx, then the string constant here, K, is the stiffness. So on this graph here, what we're looking for is the gradient. So the gradient is going to give us the K. So as we see, S1 is the steepest, therefore the stiffest sample is just going to be S1, which is A. Let's now move on to the second part of the question. Okay, so in this question, it asks us which sample does not obey Hooke's law up to a 2% strain. So recall that strain is the extension per unit length. So a 2% strain on a 100 millimeter sample is going to be equal to 2% of 100, which is just 2 millimeters. So we want to look at which sample here does not obey Hooke's law for less than 2 millimeters. So if we look here on our scale, so 1 and 2, so we're looking at this line here. Okay, so as we can see, all the samples S1, S2, S3, S4, S5 are straight lines from the origin to the point of intersection with 2 here, except the last one. If we look at S5, well, it's kind of curving down there, right? So therefore we can conclude that S5 is the one that does not obey Hooke's law to a 2% strain. So that's E. Let's move on to the next question now. Okay, so in this question we want to figure out the Young's modulus of sample 3, so of this sample here. Okay, and we can assume that this cross-sectional area does not change. Okay, so let's remember our formula for Young's modulus. So this formula is given by, so I'm going to denote it by the letter E. This is stress over strain. Okay, and stress is the force per unit area, and strain is the extension per unit length. So this is equal to, FL over A delta X. So what we want to do is we want to figure out what this value is here for the portion of S3 that's a straight line. So let's look at this point here, because after that, or maybe this point might be better. Okay, let's look at this point. So let me erase that. So yeah, okay. So at this point, we now need to we know that the extension is going to be 1, 2, 3, 4, 5 millimeters. So there's an extension of 5 millimeters here. Okay, and an extension of 5 millimeters, there is a force of 200 newtons acting on it. So we know that F is 250. Now we already know the length is 100 millimeters. So let me just, so in meters, what is that going to be? So this is 10 centimeters. So this is 0.1 meters. And what is the area? Now the area is 5 millimeters by 5 millimeters. So 5 millimeters is half a centimeter. So therefore, this is 0.005 squared as the area, multiplied by the extension, which in this case we know to be 5 millimeters again. So it's multiplied by 0.005 again. Okay, so this is just 25 over, so 5 cubed multiplied by 10 to the 1, 2, 3, so 10 to the 3 times 3 gives 9. So this is equal to minus 9, sorry, okay? So this is equal to 25 divided by 125 times 10 to the 9. So this dividing through by 5 gives 1, and this gives 5. So it's going to be 0.2 times 10 to the 9, which is equal to 2 times 10 to the 8. Now this is the same as 200 times 10 to the 6. So the answer is A, 200 megapascals. Okay, let's move on to the next part of the question. Okay, so in this question, we're told that the equation for S2 is given by this expression here, and T is the tension N in N, and X is in tension in meters, and A and B are just constants. We're told that S2 breaks when its extension is 10 millimeters. Let's just convert that back just to meters, just for the sake of it. So that's 0.01 meters. And we need to find the work done when the apparatus on sample 2 breaks. Okay, so let's think about it. Whatever this thing was there, this is a force extension graph, so Fx graph. Now, let's say we had another force that was a horizontal force, constant force. Then how would we find the work done when moving from the origin to this point D here? Well, we would just do force times distance, right? But this would give us the area under this graph. Similarly, in this case, what we want to do is we want to find the area under S2. So we want to find this area shaded in black there, because the actual definition for work done is, in fact, the work done is equal to the integral of force dx. So where that just means it's the area under a force x graph, force distance graph, okay? So let's go ahead and do that. So we want the work done. So we're integrating here from the initial position, which is 0, to the final position, which is here, which is 0.01 meters. And we're integrating the force, which is ax minus bx squared, and with respect to x. Let's integrate that. So this just gives us ax squared over 2 minus b over 3x cubed. Okay, and from 0 to 0.01. Well, let's just put in 0.01. So that just gives, which is just 10 to the minus 2. So this is a over 2 times 10 to the minus 4 minus b over 3 times 10 to the minus 6. Is going to be A. So we're done with this question now.